I know, it doesn't hurt, right? Okay, we're going to look at discontinuities and rational functions today. And we're going to start graphing them next week, but we got to look at some of these things that go along with them before we can actually get them graphed. So just like a rational number is a number that can be written as a ratio of two numbers, a rational function is a function that can be written as a ratio of two functions. This is important. Shh. Okay, so it's not just that it looks like a fraction. If I have 2x plus 3 over 5, it looks like a fraction, but that's not a rational function because there's not a variable in the denominator. Does that make sense? If it's 2x plus 3 over 5x, that's a rational function. Okay, so you're going to have not just a fraction, but a fraction that has at least one variable in the denominator. So we're going to talk through most, maybe all of this is a review for you, but I think most people kind of need at least a little bit of review on this. So, yes. Yeah, yes, please. Okay, so most rational functions have restricted domains leading to discontinuities on the graph. Okay, so our types of discontinuities. We have vertical asymptotes. We've already been finding those. We were doing that yesterday, right? Horizontal asymptotes, which at least I know you know what they are. Slant asymptotes, which may be new to some of you. I kind of got the feeling that if you were in pre-AP, you did them, and if you weren't, you didn't. Is that the thing? Okay, so it's really not that bad. But what's another word for slant asymptotes? Which muscles allow you to slant? Obliques, good. So these are also oblique asymptotes. Okay, it's not like people make up these words. You never worked on your, you never worked on your obliques like when you do crunches and stuff? Why do them to the side? Huh? Yeah, me either. Can't you tell? I just know what they are. It's been a long time since I did them. All right, point discontinuities. So we've talked about those at the beginning of the year. What's another word for point discontinuities? No, but that is another discontinuity. I got that last period too. I'll get that all day, I know. But if it's a point, that means there's a hole, which means something got taken out. So that means it was, what's another word for removed? So it's removable. Oh, goodness. So I'm not sure, honestly, I don't remember which words I used more at the beginning of the year, but you need to know that could be either one. We're going to call them point discontinuities, really, but it's also called a removable discontinuity. It's the same thing, okay? And that gives you a hole. So we're going to start by talking about the holes in our graphs, or our point discontinuities, right? So point discontinuities, or holes in the graph, occur when a factor containing x, that's important, it's got to contain x, it can't just be a number, is common to the numerator and denominator. Okay, so if something is common to the numerator and denominator, that means we can cancel it out, right? So basically, anytime you can cancel something out, that's giving you a hole there in your graph. So you're always trying to factor the numerator and denominator completely. So we'll factor this, and the numerator stays x squared over, I can factor out a 3x, and that leaves me with x minus 2. Now, is there anything I can reduce? Heck yeah, I can. Okay, so these three things are being multiplied. This, and this, right? So since those are multiplied together, then I can cancel. I can't cancel this x out with this one. That's a big fat no. But I can cancel one of them out with this one. Does that make sense to you? Now, I was able to reduce it and cancel that out. However, it doesn't just like disappear. It was there to begin with, and this is the function I'm actually graphing. So when I get here, I know a couple of things before I cancel it out. X can't equal 2 because we can't divide by 0, right? X also can't equal 0. So that x cannot equal 0, period, because of what our original function was. When we reduce this, we now have that f of x is equal to x over 3 times x minus 2. You agree with that? So when you look at that one, it looks like it'd be fine if x equals 0. But this came from this one originally, so this is still important here. So this is my reduced function. Then I'm going to have point discontinuity. That created a hole. I need to find f of whatever this number is, which is 0. So f of 0, once I substitute that in, 0 over 3 times negative 2 is 0. So I have point discontinuity at 0, 0. So what this means is when we graph this, that the graph looks like this. Graph looks like this with a hole at this point. Okay, that's how you get your holes in your graphs. because when we take this original 1 and we factored it, you have a 0 down here. So if x equals 0, like if I substitute 0 into here, I'm going to have 0 over 0, and you can't divide by 0. Right, because what I'm saying is x can't equal this point. That's where the hole is. So yeah, I have to solve for that because I have to know what the y value is. Okay. All right, good. So let's look at number 2. We're going to factor. Numerator is going to factor into x minus 3 times x plus 2. Denominator is going to factor into x minus 3 times x plus 3. Is there anything I can cancel out? Yes, x minus 3 and x minus 3, those go away. So I know right here that x minus 3 cannot equal 0, because that would mean that the denominator is 0, which means x cannot equal a positive 3. So that means I have point discontinuity where the x value is 3. Yes. Because I'm putting x minus 3 cannot, yes, I get to cancel it out, but it is part of the original one. Okay, hang on. Shh. Look, this is what I'm canceling out, right? Because I'm canceling it out, but that doesn't mean it disappears and it had no effect on the graph. It exists in here. Do we agree with that? If I substitute in a 3 right now, a positive 3 right now, I would get a 0 in the denominator, and that's bad, right? So that means x cannot be a positive 3. It can't be negative 3 either, but I don't care about that yet. We're not talking about that. We're talking about point discontinuity right now. Because you have to reduce. You always reduce everything as much as you can to graph it. Always.
So why wouldn't you just put x plus 3 cannot equal 0?
Well, we can. That's true. But I'm not talking about that right now. I don't care about x plus 3. We are only focusing on what we are canceling out right now. You are correct. X plus 3 can't equal 0 either. But that's a vertical asymptote, and that we talk about right here. Does that make sense? So you're correct, and you're correct too. When you said x can't equal a negative 3, you're right about that. It can't. Are you even listening to me anymore, Parker? Yes, okay. It's like his own little world. Okay, but so, because you said x can't equal negative 3, and you're right, yeah. Yes, obviously it's still there. So yes, but you're correct. X can't equal a negative 3 either. We're just not talking about that yet. So x can't equal 3. So right, I'm saying it can't equal 3, and then I'm solving for it because I have to figure out where it can't be, because that's where my hole goes. You with me? So x cannot equal 3, but I have to figure out what the y value is when that happens, because the y can't equal that either. So f of 3, oh, well, it'll help if I finish this out, sorry. F of x, once I reduce, is x plus 2 over x plus 3. This is my reduced function. So the graph looks like this, but is going to have a hole here. So when I substitute that in, that's going to give me 5 over 6. So it's 5/6, and that's where my hole is. Okay? Does that make sense? Okay. So you are correct. We don't get to just ignore the x plus 3, but we just are right now because we're only talking about point. No. I substitute a 3 in. This is the x value that I'm concerned with. I substituted in a 0 up here because x can't equal 0. You get with me now? Whew. All right. So let's look at number 3. I'm going to factor in the numerator. I'm going to factor out a 2x. That leaves me with x minus 3. In the denominator, I have a 2x. I can cancel out the 2x, which means x cannot equal 0. Like you've got to come up with that before you cancel it out, so it's not like gone and you forget to even worry about it. So I cancel that out, so I get f of x is equal to x minus 3. Right? So my function is I'm going to graph a line, basically. And then I'm going to have point discontinuity at 0, and then I have to find f of 0, which is going to be negative 3. What do you mean? Oh, this would have been, because it's in the denominator, this is a vertical asymptote. Is that what you're asking? Yeah. Okay, everybody okay on the point discontinuity so far? Yeah. All right. All right, now let's look at vertical asymptotes. So vertical asymptotes occur when a factor, again, containing x, it's not just a number down there, is unique to the denominator. Okay? That means it only exists in the denominator. That's why we have to reduce first. So, can I factor or reduce this at all? No. So what we know is that we cannot divide by 0. So x plus 2 cannot equal 0, which means x cannot equal negative 2. That's why we have an asymptote there. There is a vertical asymptote at x equals negative 2. Right? Because x cannot equal negative 2. That's an equation of a line. That's why it has to be written that way. An equation of a vertical line. Okay? Good. Okay, we're good? All right. So now let's look at number 2. I'm going to factor the numerator. So this gives me x plus 7 times x minus 7 over x minus 7. So I can reduce, right? When I reduce, I say that x cannot equal a positive 7. That means that doesn't give me a vertical asymptote, right? That gives me a point discontinuity. Point discontinuity at 7 something. We'll figure that out in a minute. Once I reduce, I have f of x is equal to x plus 7. Where did I lose you? Because I canceled it out. Because yes, there's something down there, but it's not unique to the denominator. And so that's what makes it a point discontinuity. So I'm going to graph a line. Do I have any vertical asymptotes? No. So vertical asymptotes, there are none. And then I have to find f of 7, which is 14. So I have a point discontinuity at 7, 14. And I know they didn't ask me for that either, but since we've already talked about it, we'll go ahead and write it in. They only come from the denominator after you have reduced the function, but yes. So the zeros in the numerator are the zeros of the function. The zeros of the denominator are your vertical asymptotes. Okay, does that make sense? Okay, anything else? You just put none, yes. No, you wouldn't have to. If all it was asking for, I should have done that. If all it asked for was this, that's all you'd have to put. I wanted to make sure we knew why it was something else. Okay, let's look at number 3. So I need to factor. Factor out of 2, that leaves me with x minus 4. Denominator, I get x plus 4 times x minus 4, thank you. Can I reduce anything? Yes, so these cancel out. X cannot equal 4, right? And x also cannot equal negative 4. Would you agree with that? But they're for different reasons, right? My reduced function is 2 over x plus 4. So these are two different reasons here. I canceled out the x minus 4, so that means I'm going to have a point discontinuity when x is 4. I'm going to have a vertical asymptote when x equals negative 4. Okay, so there's that. And then I find f of 4 in my reduced function. It's going to give me 2 over 8, which is what? 1/4.
So, Miss, if we go back to like number 1.
Okay, let's go back to number 1.
So since x minus 2 is still at the bottom,
yes.
Is that also vertical asymptote?
Yes, so this right here, and I didn't put on there because we hadn't talked about it yet, but yes, right here you have a vertical asymptote at x equals 2.
So the only one we wouldn't have a vertical asymptote at would be number 3.
Exactly, because here we would have a vertical asymptote at what? Negative 3. Okay, is that? I'm sorry, say that one more time. No, because there's no variable there. Because all that's going to affect things is, because whether it was 3 times x minus 2 or 3x minus 6, still I would get the same thing. Because we would say like 3x minus 6 cannot equal 0, right? So we'd say 3x cannot equal 6, so x cannot equal 2. I still get a 2 out of that because it's just going to divide itself out. Okay. Good questions. Anything else? All right. Let's go down to number 4. It's already factored for us, right? Can I reduce anything? No. Do I have a vertical asymptote? Yes, I actually have how many? 2. Because I know x cannot equal 0 and x cannot equal negative 5. So I have vertical asymptotes at x equals 0 and x equals negative 5. Okay? We all okay with that? Yes, yes? Okay, good deal. Let's flip it over. Okay, so now we're going to look at horizontal asymptotes. 3 things can happen when you have rational functions. They can be top-heavy, bottom-heavy, or tied in degree. And we're talking about the degrees of the numerator and denominator. So vertical asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator. So if it's top-heavy, it's not greater than or equal to, right? The numerator would be greater when it's top-heavy. So if it's top-heavy in degree, greater degree in the numerator would indicate no horizontal asymptote. So if you have a rational function and the degree in the numerator is bigger than the degree of the denominator, you have, for your horizontal asymptote, the answer is none. That means, well, not more variables, it's the degree. This is the degree 2, so this is degree 2 over degree 1. It's the degree. No, you don't have to do anything. No, there's nothing to solve for it. So this is degree 3. Oh my gosh. Degree 3 over degree 2. So since this number is bigger than that number, we're just talking about the degree of the function. There's none. There's no work, there's no nothing. We do not have a horizontal asymptote. We're getting there. Hang on. If it's bottom heavy, so here I have degree 0 in the numerator over degree 1 in the denominator. And here I have degree 1 over degree 2. So do you see how it's bottom heavy? The degree of the function is higher in the denominator. So if it's bottom heavy, greater degree in the denominator, indicates horizontal asymptote is y equals 0. There's no work there either. Okay? It's just if it's like that, your horizontal asymptote is y equals 0. I do care. I'm glad that you remember. All right. No, they are not. Tied in degree leads to a horizontal asymptote where y equals the ratio. Ratio means we're getting a what? Fraction of the leading coefficients of the numerator and denominator. So this is degree 1 over degree 1. So all I look at is these leading coefficients. That means that your horizontal asymptote is what? 2 over 5. It's y equals 2/5. Okay? And then the next one is 1. Horizontal asymptote, I look at 2 over 2, so y equals 1. Okay? We could? You got it? No, it's because this is the second, it's because I'm pulling it out of a different part of your brain. She was putting it into your brain. I am knocking off the cobwebs and pulling it out of your brain.
Let me just cram these 3 packets.
Oh, stop it. Okay. Slant asymptotes. So this might be new to some of you, but it's really not that big of a deal. So let me show you here real quick. Now, you'd never have a graph that actually looked like this. It just kind of is everything in one. But we have our horizontal asymptote, right? So that means that like this comes up and it hugs that horizontal asymptote, and it can come down here and hug that horizontal asymptote like that, right? Then we have a vertical asymptote. So this is what's hugging that vertical asymptote like that. Then we have an oblique asymptote, or our slant asymptote, this dotted line. So that's what's happening with this function. It's coming and it's getting closer and closer and closer to that oblique asymptote. It doesn't, because like I said, this isn't one function. It's not even a function because it wouldn't pass the vertical line test. It just kind of has all the different things on there so you can see them. Okay? But no, it's not one function because it's just like wacky. Yeah. But there will be some crossing of asymptotes that we get into, because remember that's something I kind of threw out at you earlier. You're like, what? You can cross an asymptote? Yes, you can. And we'll talk about when and how and whatnot. All right, so let's go back to these slant asymptotes. They occur when the reduced rational function contains an x in the denominator. And the numerator is 1 greater in degree than the denominator. Okay? So we look at this and we go, all right, so it's top heavy. Since it's top heavy, there is no horizontal asymptote. But there could be a slant asymptote. It doesn't guarantee it, but it could be. So then I have to reduce this, right? So I'm going, or see if I can reduce it. I'm going to factor the numerator. This is going to factor into x minus 1 times x minus 3, all over x minus 2. Can I reduce that at all? No. Okay, so the reduced function contains an x in the denominator. And the numerator is 1 greater in degree. So we already know it's greater, but it is only 1 greater. So this means I'm going to have a slant asymptote. We figure that out by dividing the numerator and denominator. So I can either do long division or synthetic division. Which one would you choose here? Synthetic? I would choose synthetic myself. I would choose synthetic division. So we're going to do 2. And this is going to be 1, negative 4, and 3. So I bring down the 1. This is 2. Because we are supposed to be dividing the numerator by the denominator. So because I said so. Negative 4 and then negative 1. Now, you're going to get a remainder. If you don't get a remainder, then you should have canceled something out, right? We don't expect it to divide evenly. Okay, so those of you that did do slant asymptotes, when you get a remainder, do you remember what you do with it? Okay, that's okay. I was just wondering. No. Well, yes. Okay, so if we're not doing slant asymptotes, then it would be like negative 1 over x minus 2. But because we're doing this slant asymptote, you will get 1 every single time. If you don't, you did something wrong. And then you ignore it. Monday, we'll talk about why we ignore it. Because it is important in some cases, but not when it's a slant asymptote. Okay? No matter what it is, you ignore it. So your slant asymptote then is what this function is. Y equals x minus 2. That's it. Okay? Yeah. It's not bad. Okay. So now we're going to see if we can reduce this. I'm going to factor out a 2x. That leaves me with x minus 2. The denominator is 2x. Can I reduce anything? Yes, and because I'm doing that, I know still that x cannot equal 0, and what happens at x equals 0? Point discontinuity. So it doesn't necessarily ask me for it, but we're going to put it in here so we don't think we can just ignore that. So I'm going to point discontinuity at 0, and then my f of x is x minus 2, so it would be 0, negative 2. Okay? So now, am I going to have a slant asymptote? No, because it says, that's my reduced rational function. Contains an x in the denominator. Got no x in the denominator, right? So it reduced, and my slant asymptote is going to be none. Yes, if it's more than 1 degree greater, then it just doesn't have an asymptote. Okay. All right, so let's see. Even if I could factor the numerator in number 3, would I be factoring out an x that I could cancel in the denominator? No. So maybe I can factor it, maybe I can't, but I don't really care because it's not going to cancel out what I need anyway. So I can't reduce it. So that is my reduced version. It has an x in the denominator. So now I need to divide, right? And so this leading coefficient is not 1, so I do not get to do synthetic. I got to do long. So 2x is going to divide into 2x squared minus 4x plus 3. So 2x goes into 2x squared x times. So it's 2x squared. Then I change my signs, bring down my negative 4x. So that goes into there and negative 2 times. It's going to give me negative 4x. Change my signs, bring down my 3. So 3 is my remainder. It means nothing to me. It's gone. So my slant asymptote is y equals what I got, which is x minus 2. Which happens to be, I just realized, the same one as before, but has absolutely nothing to do with each other. Okay, everybody good so far? All right, so now let's look at the number 4. Can I factor the denominator? No, I need 2 numbers that are going to multiply to give me a negative 1. That's going to have to be a positive 1 and a negative 1. No way those are going to give me 2, right? And this isn't going to factor either, so I'm like, duh, I can't do anything else. Which means and this is 1 degree higher, so I need to divide. What's your only option for division here? Long division. So go ahead and do x squared plus 2x minus 1. You're going to divide that into 2x cubed minus 4x squared plus 9x minus 7. Let's go ahead and do that while I hand out the assignment. Oh, what? There's an assignment? Shocking, I know. Okay, it is time to go. So in the end, like that's done, I'll get some sort of remainder. My slant asymptote is y equals 2x minus 8. Do y'all agree with that? Did y'all get farther than I did? Okay. That's what you should get if you want to finish it. The assignment, make sure you paid attention to the fact that I said front only, front only. Don't flip it over on the back and freak out because there's graphs, okay? Front only, front only. Have a great weekend.